Hello, good morning everybody. So, we are still continuing with D and F block elements, and today we will start our discussion from ionization enthalpies. Where we just want to see how a typical ionization process can be helpful in assigning the corresponding states what we are discussing so far for the formation of the metal atoms from the M which is present in bulk quantity, say iron as iron rod, iron as iron powder, to its atomic state, then to its different ionic states, where we do not know what are the typical values for N, how many electron transfer can take place and the different oxidation states what you can get, and obviously these will all form in solution. That means, in aqueous medium how we can think about the formation of the corresponding different metal ions. And as we are discussing everything related to the metals, so we will at one time we will just reach to the different metal ions also, and the properties what we are talking about for the different metal atoms. And now we will see how the different cases of ionization can think of from the corresponding charges, the nuclear charges residing on the nucleus of the metal atom. So, what we see that these changes, that means these ionization enthalpies, it can change from an left to right, where due to an increase in nuclear charge, how we can change the nuclear charge by going from scandium to copper, we are able to fill the different orbitals, and most of those cases these are inner orbitals, because if we talk about the corresponding 3D orbitals, the 4s level is there. So, we will have to knock out the electrons from the corresponding D level which are inner orbitals. And we see as we move from scandium to titanium to vanadium to ultimately say copper and zinc, the nuclear charge what we have seen so far in our previous classes, that the nuclear charge will be increasing very much, and with that increase the ionization enthalpies what we now see, the IE values, the ionization enthalpy values will also increase. And what is that particular trend if we just simply compare the corresponding metals or the metal atoms for the 3D series, for the 4D series and for the 5D series, we will see that for each of these series they change along the series of these transition elements from left to right. And the important thing is that why we should change these values, because the nuclear charge is increasing and their attraction on those electrons by those nuclear charges which are positively charged will be higher. So, it would be difficult to knock out the electron from those d orbitals. So, what we see that the successive enthalpies means successive enthalpies for each and every element. So, if we just consider, when we consider the knocking out of the first electron, so if we have scandium, then titanium, vanadium and chromium etc., what we see that due to this corresponding process of atomization, we get the corresponding metal atoms. Then the electron transfer. So, if we go for the first level of electron transfer, the first electron transfer, and all of them are taking place in the gaseous state, is not that we are having some aqueous solution or the water medium or some other solvent medium. So, if we just consider that the first electron transfer giving rise to, for the species like say chromium from the right, chromium we are getting as the monovalent state. So, the thing what is going on there for the transfer of this first electron to get the unipositive chromium is related to the corresponding ionization enthalpy for first electron transfer, and we call these as the first ionization enthalpy. So, the first ionization enthalpy is there, we can theoretically also calculate it out, or we can find out experimentally that what is the corresponding magnitude of this ionization enthalpy. Then the problem comes, or what we can compare, if we find that for all these transition elements already we have discussed that we can have variable oxidation states. So, one of the important criterion for all these species is that they are having variable oxidation states. So, what does it mean? That means if we can have a particular metal center or a metal atom such as chromium, and in solution or in gaseous state they have some stability for not only the unipositive or the monovalent species, but also the dipositive or the bivalent species or chromium 3 plus. So, the second electron transfer, the third electron transfer gives us the chromium in +2 oxidation state and chromium in +3 oxidation state. So, these will also involve some other ionization enthalpy values. So, what we see here that the bulk metal, its conversion to the atomic state and then the electron transfer for its ionic states. So, these ionization enthalpies will have some parameters which will also be related to the enthalpy of atomization, because this we see from the chromium bulk metal. So, chromium metal we have, and during that process we see some other enthalpy term. So, enthalpy of atomization. So, this is the process where from the bulk metal, if we just consider or if we can think of in such a way that we have the corresponding atomization process, and which we all know that a different thing we will also, if time permits, we will also at some point of time we will discuss something related very much to experimental inorganic chemistry or the laboratory inorganic chemistry, is our flame test. And the flame test is very much dependent on what we just looking for something testing the corresponding metal atoms. That flame tests are very useful to know that the sample, any unknown sample, whether it contains sodium or potassium or any other characteristics metal center which can give rise to color within the flame of Bunsen burner or any other burner. So, sodium and potassium, since they are very easily atomized, that means the atomization process for these alkali and alkaline earth metals are very easy. So, starting from the identification of say our common table salt, sodium chloride or potassium chloride, we all know that both of them are white in color and white powdery stuff. But if I want to distinguish that which one is sodium chloride and which one is potassium chloride, we have to do something. That means we can get these as the solid, and the solid if we from that and do the injection within the flame. So, that solid from the sodium chloride, which is Na plus Cl minus, this is also K plus Cl minus. So, large number of electrons, because we are burning hydrocarbons, we are burning some gases or LPG gases in the flame. So, the burning of hydrocarbon process will give us some idea that the flames are all rich with free electrons, because burning process which is also sometimes the flames are also we call it the reducing flame. So, these electrons basically will be helpful for giving you sodium 0 from those sodium plus inside the flame. So, similarly we can have potassium as the potassium 0. So, these are the corresponding atoms, sodium atom and the potassium atom. So, these are typically the corresponding atomized state, but we are doing something, we are thinking of the corresponding atomization process in a reverse direction or the opposite direction. There will be ions we are having, we are putting electron and we are getting this corresponding atomic state, because this atomic state when it is excited within the flame also, it will be Na0 in the excited level, Na0 star still present as atom Na0. It is getting excited. So, when we excite it by the flame also, the energy is getting from the flame, the system is getting energy from the flame. So, when it is excited, it is reaching some excited state. Then when it is coming back to the ground state again, that means Na0, it emits some characteristic flame, which is a differently color for different element. In this particular case for sodium, it is a golden yellow flame. So, the atomic state of the sodium when it is excited. So, in the excited state, it basically gives rise to some characteristic radiation and the color it is giving. So, is lambda is in 589 nanometer, which is characteristic for its golden yellow flame. So, when it emits, so basically this is a corresponding emission process, and this emission process, what we can see that this particular emission process is solely dependent on the excited state of the atoms, but we are getting these as the corresponding free atoms. So, this atomization term, which is very important and which we can apply in different places. So, enthalpy of atomization also contributes something, that how quickly or how easily with the expense of very little energy, how we can get the corresponding atomic state from the bulk metal of chromium to chromium 0. So, if we see that the ionization enthalpy for the first electron transfer, the ionization enthalpy for the second electron transfer, and the ionization enthalpy for the third electron transfer. And if we want to compare these values, what will be the trend? Because we know that in solution it is some process, that means these atoms will be also hydrated. So, the hydration energy will also contribute to the thing. So, the contribution for the hydration also will tell us that whether this chromium 3 plus will be stable in the solution or not. And ultimately we know that it can go from chromium 3 to 4 to 5 to ultimately chromium 6, which is also the reality, the group number. Group number is something and related to the group that thing, and where we can knock out all the possible electrons which is there from the D cell of chromium, giving rise to a D0 system. So, this D0 system, what we will see also afterward, that the stabilization of these other oxidation states. So, that will also tell us that though we are having the different oxidation states, that means the existence of variable oxidation states, if we just consider that okay, the different oxidation states are there, but the depending upon the nature how we get it. So, if we can just simply compare the first ionization enthalpy to the second to the third, what we see that this particular change in all these enthalpy values for the 3D elements, for the transition elements or the D block metals are completely different compared to the main group thing. That means, for the main group elements, what we see that the successive enthalpies of these elements do not increase as abruptly. So, the change is not very much, or change is not so abrupt, that means that one step to the other is not so abrupt as in the main group elements. That means, the main group elements which we call as the S block elements or the P block elements, their change is more abrupt, but in case of transition metal ions, the change is not so abrupt in terms of the corresponding ionization enthalpies. And if we just see that the successive enthalpies, that means the first ionization enthalpy to the second ionization enthalpy to the third ionization enthalpy, because we know that they exist in different oxidation states, and by getting that oxidation state at one point of time we can knock out all the d electrons. So, knocking out of all the d electrons will give you something where, like that of your chromium, chromium can go up to chromium 6 or hexavalent chromium, where no d electron is present. But if we just simply compare for the successive one as well as for a particular triad, we know now what are those triads. So, for these triads basically, as we have just compared in our previous class, the triad for say chromium, molybdenum and tungsten, this is one particular triad. Then we can have nickel, palladium and platinum. So, the d electron configurations are all same for a particular oxidation state. Only thing is that the nuclear charge is increasing, their corresponding size is also increasing. So, how quickly we can reach basically for a hexavalent chromium and a hexavalent molybdenum and hexavalent tungsten. So, within this triad basically if we consider now the IE values, the first ionization enthalpy. The first ionization enthalpy if we compare what is the corresponding trend. So, this within a particular triad, that is why we are saying that within a triad the first ionization energy is generally higher for the third than for the first and second metals. That means, if we just see for the triad like chromium, molybdenum and tungsten, what is the third one? The third one is the tungsten. So, the first ionization energy for tungsten would be higher than that of the first and the second metal atoms. First is chromium, second is molybdenum. So, what we see basically that the first ionization energy values for these metal atoms have a trend, but when we consider that a different proposition that first ionization will give you the only that monovalent species, that means the unipositive chromium, molybdenum also unipositive, that means MO 1 plus, chromium 1 plus and tungsten 1 plus. So, all these are there and we just compare for the first ionization energies. The first ionization energies for the formation of chromium in chromium 1 plus, molybdenum in molybdenum 1 plus and tungsten in tungsten 1 plus. So, there is a trend. So, these physical parameters or physical quantities is some interesting role to play, because whenever you have some data related to all these electron transfer values or the enthalpy values or the corresponding thermal energies. So, we can have always some good trend like the way we compare the melting points and the boiling points. So, how they basically related to the corresponding properties of all these metal atoms that we can see. So, this is for the first one, and if we go for the second ionization enthalpy and the third ionization enthalpy, we get chromium 2 plus, molybdenum 2 plus, tungsten 2 plus. Similarly, we get chromium 3 plus for the third, molybdenum 3 plus and tungsten 3 plus. Since size is changing and all these cases whatever trend we see for the first electron transfer, for the first electron transfer we see that the statement what we made therefore is the first ionization is generally higher for the third than for the first and the second. So, this is higher for tungsten only to get some contribution that whether we are able to knock out the first electron from the tungsten to get a tungsten in 1 plus condition. So, compared to chromium and molybdenum, the tungsten we know that is the post lanthanoid element. So, the post lanthanoid elements, there is a lanthanide contraction, the size is little bit less and the nuclear charge has increased enormously, particularly the 14 unit addition of those lanthanide elements. So, the nuclear charge effectively contracting the size. Only difference and only thing is that the 5d orbitals are little bit spatially exposed compared to 4d orbital or the 3d orbital. So, the exposure of these in space, that means the spatial exposure of d orbitals are little bit different and these are bigger in case of tungsten compared to molybdenum. But removal of this first electron is very difficult. So, that is why for this removal of this first electron for the first ionization thing, that means if we just compare for these, that means the first IE. So, the first IE for these will be the tungsten will be higher than that of molybdenum and that of chromium. But if we go for the successive removal of electrons, the successive removal of electrons will give rise to the other oxidation states. So, once you get the highest possible element in this particular triad, that means the tungsten in the monopositive state, it would be easier now to remove the second electron or the third electron, because we are removing that electron from that particular 5d level already, which one has lost its electron from this particular s level, either s level, because always we have the s2 electron center. So, s2 level and the d level, and during that particular removal, basically what we see that always we have the s2 and dn electronic configuration. This s2 and dn electronic configuration is very interesting to compare, because what we see that ground state electronic configuration we just compare, then at one point we are just comparing the corresponding electronic configuration for the ionic state what we are present or we are getting in solution. So, once this first electron is removed for the first ionization energy, that means it is S1 and Dn, and the relative ordering of these levels, suppose this is 4s for chromium, if we are considering this for chromium, this is 3d. So, the electrons what we are trying to move from there is that we are removing this electron. So, we are having this electron in the 4s level. So, we knocked out these, and at the same time when initially in the ground state we have some energy gap between these two levels, if we say, and after removal of these, this energy gap may not be the same. There is some change in this particular relative energy levels for this 3d and 4s level, and that is why when we move this particular electron from this level, that means s level to s1. So, these two are basically, these two energy levels are going very close to each other, and this particular removal, so if they are very close and if they are merging to each other, this s electron can go to the d level, because there is no s therefore. So, s will be therefore 0 and d will be dn plus 1. So, the successive removal of all these electrons from the first to the second and to the third, once we remove the first one which is removed from the s level, but the subsequent electrons, if the reorganization can take place, we can have some gain in energy through that reorganization energy, and that reorganization energy will help us to say that whether we have the s level is empty, only the d electrons we can have for getting the second ionization energy and the third ionization energy. So, the second electron, the third electron and so on are going from this particular d level only. So, d level are there. So, not only reorganization energy, so we can have some d orbitals, more number of d electrons in these levels we can have. We know that the starting point we have the 6 electrons are there. So, we also consider the corresponding in contribution for exchange energy. So, exchange energies are there. So, that is why the what trend we are getting for the first ionization enthalpy is not true, and it is sometimes it is reversed, and often true for removal of the subsequent electrons. So, these are the removal of for the subsequent electrons, and the trend would be different and it is reversed also. So, what we see there therefore, that if we move from there, that means once we get these the removal of these electrons, what we will be getting? We will be getting some oxidation states, whether it is in the gaseous state or in the corresponding solution state or the aqua state. So, oxidation states, how we get those oxidation states? So, this is definitely related to the corresponding group member, and those group members are there, and depending upon the group level, that whether this is a particular group level we know from the periodic table, and this is the corresponding group number. So, all these things, that means the chromium, molybdenum, tungsten, like that of our nickel, palladium and platinum. So, we get all these things, that means the group numbers for all these things and the oxidation states. So, we can something we can assign to them as the group oxidation states. That means the highest possible oxidation states, whether we are able to achieve that or not, that we can find it out. That means the hexavalent chromium formation. So, we can go up to the removal of all the d electrons, giving rise to a 3d 0 system. So, that we will see here that is related also to the corresponding oxidation states. Just we are also discussing all these things simultaneously. So, by looking at the corresponding metal atoms, this particular table is also there in your NCERT book, and it has been taken from that book also, because it is easier to discuss from that book. If you open up that particular book, you can think of what we are talking about over here for this particular type of table only. So, we were here. So, something what is written in the bold is +3 and +6. That means these two are more stable oxidation states. So, if we just simply compare for chromium, and if we just see the chromium with molybdenum down and the tungsten more down, that we see that if we just remove more number of electrons from there, that means more number of ionization energies are involved, but the stabilization of these, how we can compare the stabilization of chromium in hexavalent state, chromium in 6 plus, molybdenum in 6 plus and tungsten in 6 plus also. So, these are all very much important related to that of your group oxidation states. So, group oxidation states is the maximum one. So, whether we get that particular group oxidation states which is the maximum one, and we see that the corresponding species what we are getting, that means we are just taking all the electrons from its corresponding influence of the nuclear charge, and the metal ion center will remaining as the hexavalent one. So, it will also be electron greedy, that means it would be highly correspondingly it has the electron greediness and it will be highly reducing. But what about the corresponding other one? So, the nature basically. So, this one, that the corresponding nature that is goes for the electron corresponding electrons what we are getting from there, that the number of oxidation states. As we move that for scandium, it has 1 electron in the d level. So, if we remove all 3 together for the 4s2 and 3d 1 electron, we get the trivalent. So, that is why scandium has only 1 oxidation state, which is whether we call it as a most stable one or the not so stable one is there, does not matter, because we are not able to have some chance to compare with the other oxidation states. Similarly, that is true for zinc, and in case of zinc it is written in bold and is not written in red. So, the scandium in trivalent state is not so stable compared to the corresponding oxidation state for zinc as zinc 2 plus, because the situation is also very much similar for zinc 2 plus, where only 2 electrons you can remove from the S cell 4s cell and leaving behind with a 3d10 electronic configuration, and 3d10 electronic configuration is the stable one. So, for all these cases like that of our manganese, we have seen that in KMnO4, the potassium manganate 7 or potassium permanganate, again we can remove all the electrons from its sphere of attraction of the nuclear charge. The manganese can go up to a heptavalent state, that means the +7 oxidation state. And in case of manganese also, we just write that the +2 and +7 are stable. So, when we see that the manganese and the different redox reactions, if we just consider the different redox reactions, so for these redox reactions, now we just slowly moving to the ionic reactions. So, these redox reactions, if we just comparing the corresponding properties of KMnO4 in solution, whether we are comparing it in the acid medium or in the basic medium or in the neutral condition. So, whatever solution we are handling, that is important for the electron transfer reactions, but since this is a species where your manganese is in the heptavalent state, manganese is in the +7 oxidation state. So, definitely it will be reducing. So, it will just basically just go for the center will be reduced rather, and it will just accept corresponding electrons. So, this is a typical oxidizing agent. So, for the redox titrations, the permanometry also we have seen. In the redox titrations, we use this manganese as the manganese 7. So, it has the corresponding thing that where you can reduce. So, it can reduce for all these oxidation states. So, just now we have seen that you can have an oxidation state from +7 to +2. So, this is +7. So, +7 to it can go to +6, +5, +4 to +2. So, when you reduce it, so manganese in acidic medium, in this particular medium when you have H plus, plenty of H plus is there, that means this species which is corresponding the aqueous species, and if we have all the water molecules, and the most common one is the 6 water molecules bound to this manganese center when we do it in aqueous medium, in the water medium. So, this binding, so in the acidic medium only it can supply these water molecules. So, that is why this particular species is present, that means the +2 oxidation state for manganese is stable in acidic medium, but in the neutral condition or in the basic medium, before that, in absence of a large amount of H plus or plenty of H plus, what we will have? We will have either H2O, or the self dissociation of H2O also can sometimes give hydroxide ion, because we all know when we have water we have both H plus and OH minus. So, when manganese is reducing stepwise and at one point as going to say +4 oxidation state. So, when it is in +4 oxidation state, more electron transfer can take place to reach to +2, but we are reducing that particular center, that means the heptavalent manganese in a stepwise manner. So, one electron is putting to +6, another electron to +5 and the third electron to +4. So, once +4 is forming, that means manganese in +4 oxidation state, that means the tetravalent manganese is there, and in the system has more number of hydroxide ions and all these things. So, immediately what we think that the species will slowly attract these hydroxide ions, because this is positively charged and the positively charged is not that much, that means 7 plus for the heptavalent manganese. So, this particular assembly will also try to gather there, and if basically it has some species, that means the manganese 4 hydroxide, that means Mn, this we can write very quickly or very easily, but this particular species related to its existence, its solubility and all these things. So, if it is not there, that means the hydrated hydroxide in the tetravalent state. So, similarly immediately it can just go for not giving you this particular species, because you can have further deprotonation from this HO minus. So, what we have earlier, we have water molecules in our hand, that is getting or giving you HO minus to removal of one proton, and the removal of the second proton will give you O2 minus. So, at one point of time, if you have bound hydroxide to manganese 4 center, the tetravalent manganese center, and this OH bond, because this manganese is bound to this particular tetravalent manganese through these lone pair of electrons. There are more number of lone pair of electrons on the hydroxide ion. So, the more number of electron pairs it has, so it will basically attract more this electron density, because is already manganese is in not in +2 oxidation state, it is in the tetravalent oxidation state. So, it basically pulling towards that particular site. So, the pulling of this electron density to the manganese center will give rise to some unique observation, that is your pKa of for this removal of the second proton, that means the pKa of this is going down, and this lone pair which is responsible for this particular bond, keeping up this particular bond, is moving towards this O. So, you have the chance. So, the pKa is lowering and your this H is removed from here as H plus and O will stay there as O2 minus. So, this is the particular situation which is arising even in the bound form of manganese, if we are thinking that the theoretically possible species is manganese 4 in the hydroxide, which is not physically observable. Only thing that from there immediately within the same oxidation state, the manganese will be removed as MnO2, because it has less amount of proton because it is not acidic medium, it is alkaline medium or the neutral medium. So, protons are not there. So, we are not forcing to protonate these oxides which is bound to the manganese center, and the manganese oxygen bond is very strong now, and we are leaving behind with the corresponding separation of this manganese dioxide or the manganese precipitation is there. That means, manganese dioxide will be precipitated from that particular medium. So, we see that a particular redox reaction, what we will be talking about, whether the condition is acidic or basic, we get that we will just at one point we just stabilize this particular reduced form of manganese in the bivalent state. In other case, we will just simply stay at the tetravalent state of manganese dioxide. So, we just see that this is also true for all other cases like that of our iron. Iron, we all know that the two oxidation states, the 2 plus and 3 plus, the ferrous state and the ferric state we always have. Even in the mineralized condition, the nature is also giving us this particular form in corresponding hematite and magnetites. So, these oxide ores are there. Similarly, for cobalt also the +2 and +3. So, we see that most of these cases starting from manganese to nickel to zinc, we have the stability which are written in the bold. So, they are all in bivalent state. So, this particularly which is also true for copper, copper is also in the bivalent state, but the copper can also be reduced to copper 1 plus, which we also know the cuprous oxide Cu2O. So, these basically go for something where we see that the elements which give the greatest number of oxidation state occur in or near the middle of the series. Why this particular area? That means chromium to iron basically. So, the chromium to iron, we have more number of variable oxidation states. So, which are very much true for the corresponding property of transition metals, that they have variable oxidation states. So, variable oxidation states in terms of the large number of oxidation states, which is aptly fitting with that of our chromium, molybdenum and iron, which are close to the middle of that particular series. So, that is why they are giving all these different oxidation states. So, as we move for electron transfer for the atomic state or the gaseous atomic state, we also can talk about the corresponding electropositivity. That means, when we move for the corresponding increasing ionization energies. So, as we move for increasing ionization energies, there is decline in electropositive character. Since the ionization enthalpy is very less for alkali and alkaline metal atoms like sodium and potassium, they are well known for us that they are the electropositive metals. So, we see therefore that what about these, that is why as we move, as we go down, that means for considering the second ionization enthalpy and the third ionization enthalpy, we see that though we are getting this, chromium will be getting, when we go for the typical examples for these chromium centers in chromates as well as in dichromates, which are highly oxidizing and we use for the redox titrations, titrimetric analysis of some reductants. But what about this molybdenum and tungsten? Because of their large size, we see that these are very much stable, and the stability of these things will be there, that these latter elements, they are also from the elemental state also. What we know that the noble metal atoms or the coinage metal atoms, those are the heavier metal atoms also. So, similarly in the ionic states also. So, these ionic elements which are in the latter part also basically, so they are not so reactive in terms of the reactivity pattern or the redox potential value for the chromium 6, because the chromium 6 is there, you know, that is the chromium 6 is the stable oxidation state, and the chromium 3 when we settle between this trivalent and the hexavalent state, we know the corresponding E0 for chromium. So, if we are just thinking of something where we have the corresponding E0 value, the potential for the electron transfer for molybdenum as well as tungsten, which is also very simple to understand, that we will discuss in detail in our next chapter, where we talk about the corresponding coordination compounds. But the example what we can take very simple, just now we have discussed for manganese, that if we go for some stabilization of manganese in the tetravalent state compared to manganese in the bivalent state, that means this manganese is the manganese 2 plus. So, this manganese as manganese 2 plus, which is stable in acid. So, in acidic medium this Mn2 plus is stable, but this MnO2 is stable in basic or neutral condition, basic or neutral medium. So, what we see that if we just compare these two, that means the bivalent state and the tetravalent state, and in our previous class what we have commented somewhere that the stability of these, that means the stability of these can take place in the higher oxidation states for harder anions. So, O2 minus we have classified as an harder anion like that of our fluoride, chloride itself, but O has a charge, O2 minus has a charge, higher amount of charge, and size is also less. So, it is more harder than the other species which is uninegative like fluoride, chloride, bromide and iodide. So, this particular one which can be stabilized. So, harder anions can stabilize the higher oxidation state. Higher oxidation state in terms of the oxidation state what we are comparing with that of our bivalent state of manganese. So, the binding of this O, that means O2 minus, will stabilize this particular manganese in the +4 oxidation state, which is not available to stabilize this particular manganese, because simply from manganese 4 plus to reduction plus 1 electron to manganese 3 plus to manganese 2 plus is taking place very quickly to ultimately reach this Mn2 plus in acidic condition. So, this is not getting to bind this particular one, even if you have some interaction like this what we just now I have shown you, that if you have a discrete MnOH bond, that we will discuss again in detail in our coordination compound classes. So, this is there, and if we just see that the medium is acidic, so you can go for the corresponding protonation. It is not that this particular species, that the hydroxide ion with its lone pair of electron is binding to this manganese. So, lone pair of electrons are still available to bind H plus. What happens then? So, if this lone pair of electron is available for binding this H plus, so in acidic condition this manganese will be MnO back to MnOH2, that means the water molecule. So, water molecule as it bounds to the manganese 2, so it has no extra power of stabilizing the higher oxidation state. So, this is 4, this is 4. So, this will just simply remove, it has no extra stabilization power for stabilizing the manganese in the tetravalent state. So, this water molecule will be removed from there and we get manganese 2 plus what we are writing over here by sequential electron transfer, now 2 electron transfer. So, we are having a species which is very much stable, that means the manganese 2 plus in acidic condition. So, we see that the thing what we have defined earlier, that the stabilization of these manganese by oxide is feasible. So, when we are just now we are seeing the comparison of chromium in hexavalent state, molybdenum in hexavalent state and tungsten in hexavalent state. So, all these three and these two are more stable compared to chromium. So, you should not confuse with the stabilization to that of your electron transfer. This chromium is highly oxidizing, that we will discuss when we talk about the corresponding standard electrode potential or the potential for electron transfer from the manganese as manganese 0 or any other lower oxidation state. So, E0 is higher for this, but for these two cases the E0 is lower, but the stabilization is something different. So, stabilization, that means the higher oxidation states are stabilized altogether for the higher member of that particular group, the way we have discussed earlier, the series of iron, ruthenium and osmium, and what are the different oxides which can be stabilized for that. So, this particular one, but what effect we are just trying to explain over here is that the effect of this O2 minus. So, once you just see that this particular species, what we will be getting, that in the stabilization of this molybdenum in the hexavalent state and the tungsten in the hexavalent state, and if we do all our reactions in the aqueous medium, in the water medium or some mixed solvent medium or the water alcohol medium, what we see that this particular one, like same thing, the thing what we are now discussing, we are concentrating our attention on the particular type of bond which we all the time getting from coordination of water molecule also, because the MO bond is there, MO bond is always there if you have bound water molecules. We all discuss all this in detail again, that if you have a typical metal salt like that of our nickel chloride or copper chloride, we dissolve it in water and immediately the corresponding aqueous species are forming, the aqueous species are forming in solution. And all these aqueous species, why they are forming? They are forming the corresponding coordinate bonds, and those coordinate bonds, why they are forming? Because you have a typical or a definite structure, definite geometry for a particular arrangement where you have M and O bond. So, MO bond is there. Similarly, in this particular situation, what we have seen just now over here, that means M and OH. So, metal is there, it can be chromium, it can be molybdenum, it can be tungsten. So, for hydroxide also you have MO bond, and for oxide also you have MO bond, but the nature is always different. So, this particular one is the longest one, because you have this water. So, the neutral species, the species is typically neutral, no advantage from the charge, only the lone pair is interacting with the metal center, and obviously the metal charge is also play an important role, how good that particular center to attract the lone pair from the water molecule, because these water molecules are getting polarized, because the polarization is there. So, is a covalent molecule, these water molecules are typically covalent molecules, but there will be a charge separation. So, hypothetically you can have, initially you can have delta delta minus charge separation from this delta plus and delta plus charge separation, but finally what we can see the full charge separation for the oxide formation, and these will be remaining as H plus and O will be going for O2 minus. So, the charge advantage will be there, and due to that charge advantage, when this is going from MOH2 to MOH to MO, so this will be the shortest, the very simple logic you can have. You can also yourself, you can establish that particular logic or think of, you can satisfy yourself also that MO bond distances are decreasing. So, the decrease in these MO bond distances will tell you something, that you can have other lone pair of electrons, and is not that this particular condition or the situation is very much similar to that of our mononuclear entity. It can be binuclear, it can be trinuclear, or it can be a corresponding polynuclear type of thing. The way we get, that means the oxide, what we are talking about this MnO2 we all know, because the metal goes for the metallurgy, and the metallurgical people are also talking about, is basically a subject which dealt by the metallurgists, and these metallurgists can think of in such a way that the same oxide bond formation can take place, and this we all know is a mineral or ore for manganese, which is pyrolusite. So, what we are getting from the solution as this manganese in the tetravalent state, from the solution we are producing from KMnO4 is the same type of thing. So, nature is also doing whenever the nature is getting manganese into the system. So, you see that this is not so unusual oxidation state of manganese. So, nature is stabilizing that manganese in the +4 oxidation state, like that of the stabilization of iron oxidation state in the ferric state for Fe3O4. So, this one, but this is not a mononuclear entity that you can have one manganese and two oxide groups are attached to that manganese center. So, it is a polynuclear matrix type of arrangement, and you can have more number of bridging groups. So, this oxygen, so this oxide we can have, and that particular oxide can give rise to something where we can have the initial sharing of this lone pair can bind two of these metal center, the same metal center, one is M1, another is M2. Also we can have another as M3. So, this entity, which is very interesting to know, that this particular entity for a trinuclear system, this is there due to the same O, which is your oxide only. So, oxide can hold 3 metal centers together, that is why the networking, the matrix, which is also possible for other oxide minerals, because the large number of oxide minerals we can have. So, this oxide can give rise to, so instead of getting one single MO bond, we are getting 3 MO bonds. So, when if we have some discrete MO bond for this, so that particular discrete MO bond, you know that corresponding MO bond character is completely different. So, if we have the terminal and the discrete MO bond, that particular MO bond we can consider it as a MO double bond. So, MO double bond is there because this distance is very short and the shortest for multiple bonding also, because for water you cannot have a double bond. Hydroxide also you cannot have immediately the double bond, but for the oxide we can have a double bond because it is a very compact arrangement. And most of these cases, when you go from these through the removal of this H as the H plus, what we get that the oxide and this particular one, if the orbitals are available on this particular metal center or the metal ion center, depending upon its charge or the oxidation state, we can have the corresponding double bond character. So, two things we are discussing over here, that how we can stabilize using the harder donor atoms, the higher oxidation states, and the corresponding binding of the oxide ion. So, oxide ion binding is pretty important to stabilize this particular center, such as if it is molybdenum and tungsten, we have the corresponding oxidation state as the stabilization of the hexavalent manganese center. So, what we get there basically, therefore, that we just commented over here that molybdenum 6 and tungsten 6 are found to be more stable than chromium 6. So, how we can just simply explain this particular line, this particular statement, that chromium, we all know that the chromium is 6 is in chromium oxide also. We know that this is stabilized by oxide only, and this is the chromium hexavalent state. So, there also you can have some multiple bonds around this chromium and its stability in the solid state. But once we go and once we produce this as in the solution state, we know that CrO4 2 minus, which is also again a hexavalent chromium center. So, that hexavalent chromium center we can have, and this chromium has 4, this is a mononuclear species, well known mononuclear species, has 4 chromium oxygen bonds. So, we cannot have some network or we cannot have some corresponding matrix formation for the corresponding oxide type of thing. And we at the same time, depending upon the chromium oxygen distance, we know that there is no chance of getting you or giving you or putting you to a corresponding chromium oxygen multiple bond. So, chromium oxygen multiple bond is not the thing what is forming over there, but as we move down to molybdenum and tungsten, again in the hexavalent state molybdenum 6 and tungsten 6. Now, we see the proposition what we are discussing just now, that for that 3-dimensional system or a matrix type of system, what we can have for these. So, molybdenum always will have some affinity, that means even the free condition also, that this is particular species is very much stable. Instead of talking in terms of the stabilization of Mn plus in presence of say water or some aqueous medium, there is no necessity to give you an alkaline medium or the supply of the hydroxide ion. If the system is greedy or the system is stabilized using hydroxide ions, it can generate those hydroxide ions which are required for stabilizing this particular species from the water molecules itself. So, getting those from water molecule itself as the hydroxide ions, and finally, what we get that this molybdenum, if it has the hydroxide groups attached to it and this particular pK value is changing. So, again like that what we have discussed for manganese is very simple to apply over here also, that you get that you go for the corresponding deprotonation and this molybdenum center can have a molybdenum oxo bond. So, this particular stabilization is that. So, instead of talking the same molybdenum center where N value is equal to 6, we say, so this is also a hexavalent molybdenum center. So, is not that the molybdenum size of molybdenum as well as the tungsten also the size is a little bit bigger. So, there is no competition or the steric crowding for putting one oxo over here and opposite to that center as another, that means trans to each other. So, these two are trans to each other 180 degree apart can be utilized. So, this particular unit similarly for molybdenum also it can be trans or it can be cis also of 90 degree separation. So, this can be cis also. So, the same entity what we are trying to say over here is that the same entity what we have discussed earlier in the previous slide, that the stabilization of MnO2. So, but is not discrete, is not that it is the mononuclear manganese dioxide is giving you like this. So, this particular matrix for large number of oxides and the large number of species what we can have, and even in the complex chemistry, the coordination complex formation we will see also that very quickly we can stabilize this manganese or the tungsten in hexavalent state by putting one oxide or another oxide is this particular species. So, getting this molybdenum. So, instead of talking in terms of the corresponding say molybdenum in hexavalent state, tungsten in hexavalent state, similarly for other species like vanadium also we will be talking about vanadium plus 4 plus, as well as the non-transition elements also, that if we can, we know that is a laboratory reality also. In the laboratory experiments we use sodium bismuthate NaBiO3. At one point we have discussed during our redox reactions that NaBiO3 is there. So, again large number of oxides around bismuth. So, all these things can very nicely be stabilized because these are not their lower oxidation states, stable lower oxidation states. So, simply this particular one can be stabilized by their corresponding oxo bonds. So, like this. So, we consider that this particular entity is stabilized as the corresponding molybdenum species, this particular part is stabilized as the vanadium species. Similarly, the tungsten double bond oxygen and the bismuth double bond oxygen is also a reality. So, this entity is so stable, that means the molybdenum oxygen bond and the tungsten oxygen bond is stable, is so stable that even in the strong acidic condition it is very difficult to kick out this particular oxygen or this particular oxygen from their corresponding species, which is molybdenum or vanadium. So, the bare thing we won't get. So, instead of getting that we get this oxygen. So, very quickly we get this. So, this particular, so if we have any other species, that means the charge neutralization, the 4 charges due to this O2 minus and this O2 minus is balanced, only the overall charge remaining will be 2 plus. So, some other group or some other ligand can come and bound to this particular species, and effectively what we will be getting, effectively what we are getting as that of the corresponding species is a bigger size, but the charge is small like that of our nickel, manganese 2 plus, nickel 2 plus or copper 2 plus. So, we will just continue from here in our next class, that how the different oxidation states and assigning the oxidation state to the species, but we should not forget at any point of time where we are in the periodic table, because the size and their position in the periodic table will guide us where we can go from manganese to any other species, manganese to any other species, as well as the chromium to any other species and the different oxidation states. Okay, thank you very much.